Okay guys, a reminder of my office hours, 1:30 to 3:30 Tuesdays in Hamilton Hall 403. So if you come and you don't see me, I'm probably just like grabbing a snack or in the washroom or something, but you can send me an email and I will rush over. You know, it's a long time to stay still for 2 hours if no one's coming to visit me. So if I'm not there, send me an email. I'm definitely nearby and I'll come see you. So yeah, is there anything in particular you guys wanted to talk about today? Okay, if not, we'll go ahead with my plan. So how much have you guys been, like, how much have you guys spoken about sequences yet? Have you guys spoken at all about sequences yet?
We just got to like convergence.
Okay, we just got to convergence, like last lecture.
Like 3.1 is pretty much always over.
Okay.
I swear. Oh, that's not.
No, I think we're
Okay. Do we want to talk about sequences today? Because I kind of prepared, so my other tutorial is on Monday, and I prepared all my content to be about sequences, but they hadn't even seen it yet. So then we ended up talking about something else. Okay, we'll do one not sequences question and one sequences question. So I noticed some of the questions, some of the homework problems, or not homework, practice problems used this Archimedean property thing. So I thought I would just go over an example of what a proof with the Archimedean property would look like. So in the textbook, this is 2.4.3. It's called the Archimedean property. I'm not sure if I'm spelling this right. With an I. Archimedean property. So I thought I would just go over one or two proofs using this thing. So first let's talk about what this is. Okay, so someone name a real number. Any real number. There's a lot of choices. There's no wrong answer here. Someone give me a real number. 1. Okay, 2 is bigger than 1. Someone name another real number. 4? Is that what you said? Does someone say 4? Did I hallucinate? Okay, 5 is bigger than 4. Okay, one more guys, one more. 7. Okay, 8 is bigger than 7. So what the Archimedean property says is for any real number, there exists a natural number greater than that real number. Okay, so that's the Archimedean property. Give me any number, and I can find a natural number which is larger. And it kind of makes sense. It's like pretty intuitive. Does that make sense, guys? And another way you might see it stated, so there's kind of a commonly used equivalent formulation. Actually, let's just stick with this. Okay. So I noticed 2 of the practice problems use this property. So that would be in the next section on intervals. So 2.5 questions, 7 and 9 use this property. So this is used for 2.5, question 7, and question 9. And arguably question 8. Okay. So I guess let's do question 7 so you can see what a proof with this property might look like. question 7 is like this, so let I subscript n be the interval inclusive from 0 to 1 over n, and then show that the intersection, the infinite intersection here of these INs, any guesses what this would equal? Yeah.
Just the set containing 0.
Yeah, so 0. Okay, so just to visualize the situation here, here's like the set from 0 up to 1 over 1, and then we're looking up to 1/2, and we're looking up to, okay, that this is not to scale, but this is 1/3, and then 1/4, so it's getting smaller and smaller, and it's really zeroing in on 0, right? Okay, so to formally prove this in the setting of analysis, of an analysis course, you would use the Archimedean property. And I'll just show you like how that would work. Okay. I'll write my solution here to be economical with my space. Okay, so we want to show two sets are equal. So demonstrating set equality, you have to do two things. Can someone tell me what those two things are? Yes. Exactly. So there's two things we need to do. So we need to do one, we need to show that 0 is contained in this infinite intersection, and 2, we need to show that the infinite intersection is contained in 0. Okay, so 1 is kind of the easier direction here, so let's start with that. This doesn't have any padding on it. This is just raw. Don't use this. Okay. So let's start with 1. Okay, so if you want to demonstrate a set inclusion, how would you start with that? What's the first thing you would typically do to demonstrate a set inclusion? Well, yeah.
You would take any element from the first set and prove that it must belong to the second set.
Exactly. So for this direction, we just need to show that 0 belongs to this infinite intersection. Okay. So we need to show that 0 belongs to this infinite intersection. Okay. And clearly, 0 belongs to each of the INs. So 0, virtually by definition, well, not exactly by definition. So 0 belongs to this closed interval because it's a closed interval containing 0. And this is for all n. So, because it belongs to each one, it belongs to their intersection, as desired. Okay, and this demonstrates the first inclusion. This proves this is halfway there. Okay, so for this, no Archimedean property needed. This part was a little bit straightforward. It's the next part where we'll need some Archimedean property. Okay, where am I going to write this? think I'll go up to, ooh, I know what I'll do. Okay, so I'm gonna cover up the Archimedean property now, but just make sure this is seared into your brain, because we're about to use it, okay? So for any real number, there is a larger natural number, okay? Remember that. We're about to use it. Okay, so now we're doing the second direction, so 2, right? So a reminder, here we want to show that the infinite intersection is contained in 0. Okay, so again, what's the first step here? What would the first step in demonstrating a set inclusion be? Yeah.
Pick an arbitrary element of the intersection and prove that it must belong to the superset.
Yeah, exactly. So let be an element of this intersection, and we will show that this x equals 0. Okay, and so I think we're going to do a little bit of a sort of mini contradiction here. So, suppose to the contrary, that x is greater than 0. Okay, so this next trick here is what I call a flippy-do. So other Archimedean property proofs will use a flippy-don't. This one uses a flippy-do, so you'll see what I mean in a sec. Okay, so by the Archimedean property, there exists a natural number such that n is greater than 1 over x. Okay, so that's what I mean by a flippy-do. We flipped the x over. Okay, so this is equivalent to saying that x is less that x is greater than 1 over n. So does anyone see where the contradiction might lie here?
The size is from 0 to 1 were included.
Yeah. So that's exactly it. So thus x does not belong to the interval from 0 to 1 over n. Right? This is our I sub n. Okay, so if it doesn't belong to one of the I sub n's, it doesn't belong to the intersection of all of them. So this implies that x does not belong to the infinite intersection. Suppose the contrary, that x is, yeah, so this implies that x is not an infinite intersection, but this was our starting assumption. So this is a contradiction. So we concluded that x equals 0 as desired. That would conclude the proof. Do we kind of get what's going on here? Yeah. Okay, so I say this is a flippy do because we used the Archimedean property on 1 over x. Okay, so this was question 7. So I'll just say here, this was a flippy do. This is not a technical term, which means we used the Archimedean property on 1 over x. For a flippy don't, where we don't flip it over, so for a flippy don't, look at question 9 of this section. So here you're just going to use the plain old, you're not going to flip anything over. Okay, so this is the Archimedean property. So some of the practice problems which were assigned, I think just 3 of them, but I think those were the only ones. But some of the practice problems use this property, and so now you guys know how to use it. Any questions? Comments? Concerns?
I have a quick question. Trying to remember this. I think it was 2.419, or no. Yeah, I think it was 2.419. Did they want us to prove it using like the density theorem, or was it the Archimedean property? Because like it's a really simple proof if we do it with the density theorem, but
I would say the density theorem is already, let's see, density theorem is 2.4.8. I would say the density theorem is like, it comes before this question in the textbook, and therefore it's fair game.
okay.
So you can use either one.
Okay.
Yeah. Any other questions? That looks like a fun one. Okay, so you guys just started talking about sequences, so maybe let's do, have you guys you've discussed convergent sequences, so we know what a limit is. And therefore, all these hard questions are fair game. Okay. Which one of these shall we do? Okay. I like question 7 of 3.1. Does anyone know, like, off the top of their head, when your first midterm is?
October 21st, yeah.
Okay, you guys have a decent amount of time. It's not too soon. Do you guys I should know this. You guys just have 1 midterm for this course? Okay. Alright, you guys have a decent amount of time. And that's when I can expect a lot of people to start showing up to my office hours. Okay, so, yes, I liked 3.1 question 7. That is speaking to me. Okay. Where should I write this? I'll write it here. Rude. I don't want anyone to use this, so I'm gonna like hide it over here. So 3.1. Did I say question 7? Let me take a look. Yeah, let's do question 7. But before we do that, let's just state our definition of the limit here. Okay, so a sequence of real numbers so let's call it xn converges to L if, okay, if what? Yes.
If for any arbitrary epsilon greater than 0, there exists a natural number n such that for all like little n in the sequence greater than that number, that n, the distance between the limit and xn is less than epsilon.
Very well stated. Okay. If, so let me give myself a line here. So if for any epsilon greater than 0, there exists, so I'm going to write it sort of as a function of epsilon, but you don't need to. There exists a natural number k of epsilon such that for any greater natural number, our distance is within epsilon to the limit. Okay, so we're gonna use this. It took me like maybe a year to understand any sort of epsilon or delta or whatever definition, but I got there eventually. They're kind of confusing. So now let's do question 7. So it says let, is that 7? Yeah, let xn equals, it says, okay, yeah, so ln of n plus 1. Let xn equals, and then there's 2 parts, so there's a, show that the limit equals 0. Okay, so this is just another way of saying that xn converges to 0. And then B, find an appropriate k of epsilon for, gives us 2 guys for epsilon equals 1/2 and 1/10. Okay, and so just a word on notation here. If this limit condition holds, you're going to write the limit of xn equals L. Or you might also see people write the limit as n goes to infinity of xn equals L. Okay, so that's the notation that's used when this condition is satisfied. Now, we won't get into this, but I am a math guy, and I can't help but to point out that a priori, it's not even clear that a limit is unique. That is a theorem in and of itself, that if this condition is satisfied, it's satisfied by only one L. But we won't, of course we won't do that today, but I guess my point is that there are so many subtleties at play. Okay. So, epsilon delta proof. So, epsilon delta proofs almost always start the same way. And when I'm grading an epsilon delta proof, I'll immediately give you like, I don't know, like multiple points just for writing this first sentence. So let's get into it. So the solution to A, okay, so there's one sentence you can write which will guarantee you, if I'm grading, which will guarantee you some points right away. Okay, so what would that sentence be?
Let epsilon greater than 0 be arbitrary.
Yeah, or just let epsilon be greater than 0. Be arbitrary is fine, but just that is enough. Okay, so if you have no idea how to do the proof, just write this, and already, if I'm grading, you're gonna get a few points. Okay, so let epsilon greater than 0. Okay. So we're aiming for this k of epsilon. We'll get there. So first, let's just consider the inequality at hand. So this xn minus L, in this case, this becomes 1 over ln of n plus 1 minus 0. And we're looking at when this is less than epsilon. Okay? So this is just saying 1 over ln of n plus 1 is less than epsilon. We're going to do the classic flippy do. So do a flippy do, and you get ln of n plus 1 is greater than 1 over epsilon. Okay, and so ultimately we're trying to isolate this n. Okay, so what would we do next? Not you. Okay, so we have a ln of something, and we want to isolate that something. So how do we get rid of, how do we mow the lawn? How do we mow the lawn, guys? Okay, someone telepathically told me the answer. Okay, so we're going to raise both sides to the power of e, right? So e to this power, e to this power. Okay, so raising both sides to the power of e, we get n plus 1 is greater than e to the 1 over epsilon. Important note here. Exponentiation, so raising to the power of e, exponentiation preserves inequalities. So this is raising e to the power of something, preserves inequalities because e to the x is an increasing function. Okay, so you can, if you want to apply a function to both sides of an inequality and you want to preserve that inequality, you need that function to be increasing. So when we did the flippy do, that was a decreasing function, which is why it flips the inequality. Okay. So right now we're at the point where we have n plus 1 is greater than e to the 1 over epsilon. Okay, so here we're going to get n is greater than e to the 1 over epsilon minus 1. Okay? And we want this k of epsilon we're aiming for, we want it to be an integer. So we'll just say, so let k of epsilon, okay, we want it an integer larger than this. So we're just going to take the greatest integer function. Or the ceiling function. Does everyone know what I mean when I write this ceiling function? Is that, like, just an example, like the ceiling function of 0.1 would be 1. It just looks like the greatest integer. That's the ceiling function. Okay, so so this is, let me just write that somewhere. So this is the ceiling function, aka the greatest integer function, or maybe it would be the least greater integer function. So another example, if you were to look at pi, what would the ceiling function of pi be? Good stuff, guys. Okay, so now we found what we claim to be k of epsilon, and now we're going to kind of work backwards and actually prove that this works. Or I guess we were working backwards, now we're going to work forwards. Anyway, you'll see. So, okay, again, we have our epsilon, and then we're going to fix this function k of epsilon to be the ceiling function of e to the 1 over epsilon minus 1. Just I'll ask the audience, why is this greater than 0? Okay, so maybe that's something that you can think of, but it is greater than 0. And because we're using the ceiling function, it is a natural number. Okay. And so now let's just check that our inequality is satisfied. So, let k be a natural number greater than this k of epsilon. Then, okay, the distance from xk to 0, that's just the modulus of xk. And xk was 1 over ln of k plus 1. 1 over ln of k plus 1. Okay. And so, as we make the denominator smaller, as we make the as we make the denominator smaller, we get something larger. So to make the denominator smaller, we're going to plug in our k of epsilon here. Right, so what's going on here is k plus 1 is k is greater than k of epsilon, which implies k plus 1 is greater than k of epsilon plus 1, which implies ln of k plus 1 is greater than ln of k epsilon plus 1, which implies what we have here. We do flippy-do is less than 1 over ln of k epsilon plus 1. Okay, so that's what's going on here. Okay. And so now let's apply our definition of k epsilon. 1 over ln of, so applying our definition of k epsilon, e to the 1 over epsilon minus 1 plus 1. It's getting a bit heavy here, but we'll get there. Okay, so if you think about how the floor function works, we can actually just pull this minus 1 out. So this is equal to 1 over ln of ceiling e to the 1 over epsilon. Pull the minus 1 out. Now we have cancellation here, our minus 1 and our plus 1. Ln of, so minus 1 and plus 1, we're just left with this. Okay? And so once again, so just a similar argument to what we did here. By a similar argument, can you guys see what I'm writing here? I'm just going to assume you can. The ceiling of e to the 1 over epsilon is greater or equal to 1 over e to the epsilon, and that implies the following inequality. I'm sorry, my writing is so small here. E to the 1 over epsilon. Okay, so I'm sorry the writing's so small there. And so the salient point being, here we can put a less than or equal 1 over ln of e to the 1 over epsilon. Okay, so ln of e, that cancels out. 1 over epsilon is just epsilon. Okay, so just move the furniture around and you end up with epsilon. Okay, so that was kind of a big pain in the behind, but that works. Okay. All right, so we showed that our k of epsilon works. And we're done. Yeah.
Is it like, for an assignment, for example, isn't like what you did before kind of just sufficient to prove that? Like, can't we just say like, okay, for all n's that satisfy that inequality, we know, or all n's greater than that n that satisfies that equality, that,
Just like any n using this.
yeah, like why do we have to redo it now that, you know, since we already proved it once? Or is it just for the purpose of demonstration?
I guess it kind of, what I will say is if I'm grading, you're fine. If I'm grading and you get to this point, just choose k to be any natural number greater than e to the 1 over epsilon minus 1, then you're fine. Although I would once again ask, how do you know that this is greater than 0? So any positive integer. I don't know, I guess I've certainly seen professors be a little bit extra in what they're demanding for solutions. And so some people would declare the first part. Some people would say everything we did up to here was our scratch work. And then everything after that was our proof. So some people would say that.
Also, I guess one more question.
I guess I'll just say like maybe I thought it would help to a little bit over-explain. But I think honestly you're fine if you just sort of get to this point. Yeah, that's my honest answer. Okay.
Also, is the you know, the e to the 1 over epsilon minus 1 greater than 0 a requirement if we're choosing n to be a natural number? Since it's
No, but you just have, I guess like it would be a requirement if you're explicitly defining k as a function. So, okay. So you don't need to define k explicitly as a function of epsilon like I did here. Like you could just say like k is any natural number greater than this guy. But the reason I did do this was just because of the next two parts of the question, which ask us to find like explicit. I guess maybe the solution is a little bit overworked. I'll be honest, guys. Don't hate me. I think the solution is a little bit overworked. I thought maybe it would help you guys to kind of see both the scratch work and the proof component. But the content of the proof is really making your way up to here. And then everything after that was kind of doing the same thing backwards. Okay. So yeah, I guess let's look at these last two parts here. Or they're both kind of the same. But let's just look at one real quick. Or let's look at two. It's a smaller epsilon. Okay, so let's look at 2 with our epsilon equals 1 over 10. And what we know is that we need k, some natural number satisfying k being greater than e to the 1 over epsilon minus 1. I guess, okay, we do need this. We do need this to be positive because, like, I don't know, maybe we don't. Okay, all right, okay, so Yeah, how do we find this epsilon, guys? Can we do it without a calculator? So here's our 1 over epsilon, which in this case is 1 over 10 minus 1, or just e to the 10 minus 1. Okay, that's kind of a freaking huge number. Is there a way we could like write down a k without finding without like using a calculator or anything? Because I'm kind of thinking like 3 is bigger than e, right? Yeah. Okay, so I'm thinking we just take k is equal to 3 to the power of 10, which is a like unimaginably huge number, minus 1. So like that's how you would solve this part 2, where they give us epsilon equals 1 over 10. I fear it might have caused more confusion than necessary with this solution today. Okay, do some exercises on your own. Watch some YouTube videos. Honestly, that's what really helped me get epsilon delta proofs, was watching some YouTube videos about them. That's all I got for today, guys.